The next one is called as Big Theta Notation. In Big Theta notations, our algorithms, that is T of n, is bounded in between two function here, that is C1 into G of n and C2 into G of n. Okay, our algorithm always goes within this range. It never crosses the boundary above, it never crosses the boundary below after a specific n value. A definition for that theta notation is a function T of n is said to be in theta of G of n denoted, okay, this is the expression here, T of n is belonging to theta of G of n if T of n is bounded both above and below by some positive constant multiples of G of n. Here we are using the same G of n, but the constant is different here, and our expression is always bounded within this one. Okay, that is multiples of G of n for all large n. The n value should be a very large value here. That is, if there exists some positive constant C1, this should be some positive constant C1 and one more positive constant called as C2 and some non-negative integer called as n0. Now the comparison bit of that algorithm will be done after n0. Okay, the expression is like that one. C2G of n is this one, is actually bounded below here, is always less than T of n, and this C1 of G is always bounded above, that is here T of n is always less than C1 G of n when this n value is equal to n0 or greater. That is the definition of theta notation. Now I have to prove that. Okay, now our expression actually have a function called as half n into n minus 1. Now I have to prove that is nothing but t1 here, T of n, sorry, is actually belonging to theta n square. To prove that, first I will take the upper bound of that equation here. Now half n into n minus 1 can be expanded in this way, that is nothing but half n square minus half n. This expression is always smaller value than half n square when the n value is positive value. Okay, when the n value is positive value, half n square is always greater than this value. Because n increases, this part goes on decrease. You have a decrement here. This part is always goes on decrease as the n increases rapidly. So in this case, we got answer half n square. This is the upper boundary for our equation here. Now what is the lower boundary? The lower boundary can be identified by using formula here. Half n into n minus 1 is nothing but half n square minus half n. This left hand side expression, okay, we have created one more expression at the right hand side, that is nothing but half n square minus half n into half n. This right hand side expression is always smaller than this left hand side expression because you have multiplied here 2 times here, half n. As the n value increases, this n value, this expression goes on increases. This value increases when the n value is 2 and above. When the n value is 2 and above, this expression shows smaller value compared to this value. So when you solve this formula, when you solve this right hand side, you got the output 1 divided by 4 into n square. This 1 divided by 4 into n square is always smaller than this one. Means our algorithms always bounded above on this algorithm, half, sorry, 1/4 of n square. So here the C1 is nothing but half and C2 is nothing but 1/4 here. Okay, C1 is nothing but half and C2 is nothing but 1/4. And the n naught is I am choosing here 2. Here at the upper bound n naught is 0, but at the lower bound n naught is 2. So I will pick the largest value, because here also whenever the n value reaches 2, this condition is true. Whenever the n value is greater than 2 here, this condition is true. Whenever the n value is greater than 2 here, this condition also true. So I pick the n naught here 2 here. Okay, now the C1 is half, C2 is 1/4 and n naught is 2 here.